such as rivers. This has led to unusual uncertainty in the standardized atomic weight of lithium, since this quantity depends on the natural abundance ratios of these naturally occurring stable lithium isotopes, as they are available in commercial lithium mineral sources. 30. Both stable isotopes of lithium can be laser-cooled and were used to produce the first quantum degenerative Bose-Fermi mixture. 31. Occurrence. Lithium is about as common as chlorine in the Earth's upper continental crust, on a per-atom basis. Astronomical. Although it was synthesized in the Big Bang, lithium, together with beryllium and boron, is markedly less abundant in the universe than other elements. This is a result of the comparatively low stellar temperatures necessary to destroy lithium, along with a lack of common processes to produce it. 32. According to modern cosmological theory, lithium in both stable isotopes, lithium-6 and lithium-7, was one of the three elements synthesized in the Big Bang. 33. Though the amount of lithium generated in Big Bang nucleosynthesis is dependent upon the number of photons per baryon, for accepted values the lithium abundance can be calculated, and there is a cosmological lithium discrepancy in the universe. Older stars seem to have less lithium than they should, and some younger stars have much more. 34. The lack of lithium in older stars is apparently caused by the mixing of lithium into the interior of stars, where it is destroyed. 35. While lithium is produced in younger stars, although it transmutes into two atoms of helium due to collision with a proton at temperatures above 2.4 million degrees Celsius, most stars easily attain this temperature in their interiors. Lithium is more abundant than computations would predict in later generation stars. 36. Lithium is also found in brown dwarf substellar objects and certain anomalous orange stars. Because lithium is present in cooler, less massive brown dwarfs, but is destroyed in hotter red dwarf stars, its presence in the star's spectra can be used in the lithium test to differentiate the two, as both are smaller than the Sunday. 36, 38, 39. Certain orange stars can also contain a high concentration of lithium. Those orange. Nova Centauri 2013 is the first in which evidence of lithium has been found. 37. Stars found to have a higher than usual concentration of lithium, such as Centaurus X4, orbit massive objects, neutron stars or black holes whose gravity evidently pulls heavier lithium to the surface of a hydrogen-helium star, causing more lithium to be observed. 36. On the 27th of May, 2020, astronomers reported that classical nova explosions are galactic producers of lithium-7. 40, 41. Terrestrial. Although lithium is widely distributed on Earth, it does not naturally occur in elemental form due to its high reactivity. 7. The total lithium content of seawater is very large and is estimated as 230 billion tons, where the element exists at a relatively constant concentration of 0.14 to 0.25 parts per million, ppm. 42, 43, or 25 micromolar. Winking sad smiley. 44. Higher concentrations approaching 7 ppm are found near hydrothermal vents. 43. Estimates for the Earth's crustal content range from 20 to 70 ppm by weight. 45. Lithium constitutes about 0.002% of Earth's crust. 46. In keeping with its name, lithium forms a minor part of igneous rocks with the largest concentrations in granites. Granitic pegmatites also provide the greatest abundance of lithium-containing minerals, with spodumene and petalite being the most commercially viable sources. 45. Another significant mineral of lithium is lepidolite, which is now an obsolete name for a series formed by polylithionite and trilithionite. 47, 48. Another source for lithium is hectorite clay, the only active development of which is through the Western Lithium Corporation in the United States. 49. at 20 lithium per kilogram of Earth's crust. 50. Lithium is the 25th most abundant element. According to the Handbook of Lithium and Natural Calcium, lithium is a comparatively rare element, although it is found in many rocks and some brines, but always in very low concentrations. There are a fairly large number of both lithium mineral and brine deposits, but only comparatively few of them are of actual or potential commercial value. Many are very small, others are too low in grade. 51. Chile is estimated, 2020, to have the largest reserves by far, 9.2 million tons, 52, and Australia the highest annual production, 40,000 tons. 52. One of the largest reserve bases, note 1, of lithium is in the Salar de Uyuni area of Bolivia, which has 5.4 million tons. Other major suppliers include Australia, Argentina and China. 53, 54. As of 2015, the Czech Geological Survey considered the entire Ore Mountains in the Czech Republic as lithium province. 5 deposits are registered. One near Sinovec is considered as a potentially economical deposit, with 160,000 tons of lithium. 55. In December 2019, Finnish mining company Keliber Oy reported its Rapajari lithium deposit has estimated proven and probable ore reserves of 5.280 million tons. 56. In June 2010, the New York Times reported that American geologists were conducting ground surveys on salt lakes in western Afghanistan, believing that large deposits of lithium are located there. 57. These estimates are based principally on old data, which was gathered mainly by the Soviets during their occupation of Afghanistan from 1979-1989. 58. The Department of Defense estimated the lithium reserves in Afghanistan to amount to the ones in Bolivia and dubbed it as a potential Saudi Arabia of lithium. 59. In Cornwall, England, the presence of brine rich in lithium was well known due to the region's historic mining industry, and private investors have conducted tests to investigate potential lithium extraction in this area. 60. 61. Biological. Lithium is found in trace amount in numerous plants, plankton, and invertebrates, at concentrations of 69 to 5,760 parts per billion, ppb. In vertebrates the concentration is slightly lower, and nearly all vertebrate tissue and body fluids contain lithium ranging from 21 to 763 ppb. 43. Marine organisms tend to bioaccumulate lithium more than terrestrial organisms. 62. Whether lithium has a physiological role in any of these organisms is unknown. 43. Lithium concentrations in human tissue averages about 24 ppb, 4 in blood, and 1.3 ppm in bone. 63. Lithium is easily absorbed by plants. 63. And lithium concentration in plant tissue is typically around 1 ppm. 64. Some plant families bioaccumulate more lithium than others. 64. Dry weight lithium concentrations for members of the family Solanaceae, which includes potatoes and tomatoes, for instance, can be as high as 30 ppm, while this can be as low as 0.05 ppb for corn grains. 63. Studies of lithium concentrations in mineral-rich soil give ranges between around 0.1 and 5100 ppm, with some concentrations as high as 100-400 ppm, although it is unlikely that all of it is available for uptake by plants. 64. Lithium accumulation does not appear to affect the essential nutrient composition of plants. 64. Tolerance to lithium varies by plant species and typically parallels sodium tolerance. Maize and rhodus grass, for example, are highly tolerant to lithium injury, while avocado and soybean are very sensitive. 64. Similarly, lithium at concentrations of 5 ppm reduces seed germination in some species, for example Asian rice and chickpea, but not in others, for example barley and wheat. 64. Many of lithium's major biological effects can be explained by its competition with other ions. 65. The monovalent lithium-ion Li and competes with other ions such as sodium, immediately below lithium on the periodic table, which like lithium is also a monovalent alkali metal. Lithium also competes with the valent magnesium ions, whose ionic radius, 86 pm, is approximately that of the lithium ion, 65, 90 pm. Mechanisms that transport sodium across cellular membranes also transport lithium. For instance, sodium channels, both voltage-gated and epithelial, are particularly major pathways of entry for lithium. 65. Lithium ions can also permeate through ligand-gated ion channels as well as cross both nuclear and mitochondrial membranes. 65. Like sodium, lithium can enter and partially block, although not permeate, potassium channels and calcium channels. 65. The biological effects of lithium are many and varied, but its mechanisms of action are only partially understood. 66. For instance, studies of lithium-treated patients with bipolar disorder show that, among many other effects, lithium partially reverses telomere shortening in thesiopatients and also increases mitochondrial function, although how lithium produces these pharmacological effects is not understood. 66. 67. Even the exact mechanisms involved in lithium toxicity are not fully understood. History. Petalite, Li 4010, was discovered in 1800 by the Brazilian chemist and statesman José Bonifacio de Andrade e Silva in a mine on the island of Uto, Sweden. 68, 69, 70, 71. However, it was not until 1817 that Johann August Whitson, then working in the laboratory of the chemist Jöns Jacob Bertillaius, detected the presence of a new element while analyzing petalite. 72, 73, 74, 75. This element formed compounds similar to those of sodium and potassium, though its carbonate and hydroxide were less soluble in water and less alkaline. 76. Bertillaius gave the alkaline material the name lithium/lithina, from the Greek word. Johann August Whitson is credited with the discovery of lithium in 18170, transliterated as lithos, meaning stone, to reflect its discovery in a solid mineral, as opposed to potassium, which had been discovered in plant ashes, and sodium, which was known partly for its high abundance in animal blood. He named the metal inside the material lithium. 7, 70, 75. Whitson later showed that this same element was present in the minerals spodumene and lepidolite. 77, 70. In 1818, Christian Gmelin was the first to observe that lithium salts give a bright red color to flame. 70, 78. However, both Whitson and Gmelin tried and failed to isolate the pure element from its salts. 70, 75, 79. It was not isolated until 1821, when William Thomas Brandy obtained it via electrolysis of lithium oxide, a process that had previously been employed by the chemist Sir Humphrey Davy to isolate the alkali metals potassium and sodium. 36, 79, 80, 81, 82. Brandy also described some pure salts of lithium, such as the chloride, and estimating that lithium oxide, contained about 55% metal, estimated the atomic weight of lithium to be around 9.8 g/mol, modern value ~6.94 g/mol. 83. In 1855 larger quantities of lithium were produced through the electrolysis of lithium chloride by Robert Bunsen and Augustus Mathiesen. 70, 84. The discovery of this procedure led to commercial production of lithium in 1923 by the German company Metallgesellschaft AG, which performed an electrolysis of a liquid mixture of lithium chloride and potassium chloride. 70, 85, 86. Australian psychiatrist John Cade is credited with reintroducing and popularizing the use of lithium to treat mania in 1949. 87. Shortly after, throughout the mid-20th century, lithium's mood stabilizing applicability for mania